Section 3.3, chemical equations. So now we're going to talk about how to represent a chemical reaction. Some sort of chemical reaction, representing what's called a chemical equation. So imagine lighting a match, right? So if you light a match, what happens is you get a flame, right? There's a flame coming out of it. That's a chemical reaction taking place. And what we want to do is we want to represent that chemical equation, that chemical reaction via a chemical equation. So we're going to use the symbols for the elements. And we get those symbols, of course, from the periodic table. Now, one question that comes up is, should we memorize these symbols for the period of the elements in the periodic table? And the answer is, it doesn't hurt. It doesn't hurt to know those symbols. It can be kind of helpful. It saves a little bit of time looking them up. So for me, I prefer knowing what those symbols are. And then we're going to use the chemical formulas for compounds. So for example, if we were going to say water, we would use the formula H2O. If we were going to do ammonia, we would use the chemical formula NH3. Okay? So we use symbols of the elements and then the chemical formulas for compounds. And the idea is, it's in a sense kind of like an algebraic equation. So for example, we might have this particular reaction. Represented as an equation. Okay? So what does this say? What does this equation, this chemical equation say? It says that carbon is reacting with oxygen to form carbon dioxide. Okay? That's what it's telling us. It's telling us that we have what are called reactants. These are combining with one another to form a product. And in this case, the product is carbon dioxide. Now you'll note that there are some symbols, some letters in parentheses next to the symbols and formulas in this equation. So this is a way of indicating the state of matter. So if carbon is a solid substance, we put S next to it. If it's a liquid substance, we put an L. If it's a solid substance, I already did solid. If it's a gas, it's a G. And if it's dissolved in water, we call it aqueous. And the abbreviation for aqueous is AQ. AQ for aqueous, okay? So this is telling us that we have solid carbon plus gaseous oxygen forming gaseous carbon dioxide. There's also an arrow here. The arrow points toward the products and it points away from the reactants. So in a sense, this is giving us a depiction of what happens in time. In time, over time, carbon is combining with oxygen to form carbon dioxide. So after the reaction is complete, we will have formed carbon dioxide. Before the reaction takes place, we have two separate substances. The plus sign in between those substances is there to tell us that we're adding this one to this one. Just like if we were going to bake a cake, you might say sugar plus flour plus yeast yields a cake, right? So these are separate substances that are going to be formed. I guess carbon dioxide would be one of the products as well. So we could have two substances on the product side. So that's the idea of a chemical equation. Now let's write out the chemical equation for the matchstick. Remember, we have this little matchstick, and we have a little bit of substance up here. There's actually a couple of different substances that are in the matchstick. The primary substance is sulfur. And so we could write the symbol of sulfur S. It's a solid, right? The top of a matchstick is solid. So it's solid sulfur. Now, what's it going to react with when the flame starts? You have any idea what it reacts with? That light and heat is released from that reaction. We call that an exothermic process. It reacts with oxygen that's in the air. And we write oxygen as O2. And oxygen in the air is a gas. And the product of that reaction is a stinky material called sulfur dioxide. Remember, this is a molecular substance. So we name the first nonmetal, sulfur. Then we name the second nonmetal and indicate how many there are. Di for 2, sulfide. If you want to use the British spelling, we could put PHID in there. Okay, so sulfur dioxide, I'm sorry. Where did my mind go? Sulfur dioxide, it's oxygen, right? There's 2 oxygens, or sulfur dioxide. There we go. All right, got it right there. Okay, so 2 reactants and 1 product. Notice the oxygen is written in diatomic form. So I'm going to write down here the diatomic elements from the periodic table. These are the elements that appear as diatomics, 2 atoms in a molecule. So the first one is hydrogen. So hydrogen is in the form of H2. Nitrogen is actually in the form of N2. Oxygen is in the form of O2. So I'm going to write those 3. Then I'm going to write the other 4, which is fluorine is in the form of F2. Chlorine in the form of Cl2. Bromine is in the form of Br2. And iodine is in the form of I2. So if you see a problem where they say oxygen reacts with, or oxygen is produced, you would write O2. If you saw a problem that said that chlorine is produced, or chlorine reacts, you would write Cl2. For those 7 elements, they're diatomics. Okay? You go into it in the first semester of general chemistry. Later on, it's one of the topics you discuss of why those particular elements are diatomics. Okay? So we have an equation. Let me write it in a general form. You'll see this sometimes. A plus B goes to C plus D. So that's a generic form of a chemical equation telling you that there are 2 reactants, reactant B. They're combining with each other to form 2 separate products, 2 different chemical substances, C and then also D. Okay? An example of that, just again, would be CH4, that's called methane, reacting with oxygen, again diatomic, to form carbon dioxide and water. That's the form of this particular equation. That's a combustion reaction. We may or may not have information about the states of matter. If we do, we can write those in there. G for methane, G for oxygen, G for carbon dioxide, and L for liquid, right? Liquid is L for water. That's based on information that we would have experimentally, looking at what's happening, okay? It's not necessarily obvious what the state of matter of these materials are just by looking at their chemical structures, their chemical formulas. All right, so there we go. So now the next issue to deal with is what we call balancing. So I'm going to erase Actually, let's go ahead and erase all of this. There we go. So let's talk a little bit about balancing equations. Balancing chemical equations can be pretty fun. It's a fun type of thing to do. It's based on the law of conservation of mass. It turns out that in chemical reactions, the mass of the reactants is going to equal the mass of the products. Okay? So for example, if I react hydrogen, and let's say that I have 4 grams of hydrogen, that's the mass, right? Grams. And I combine that with oxygen, they would combine to form water, and the amount of water that we would have, I'm sorry, 32, let me get this wrong, 32 grams, sorry. Let me erase that just so that it's correct. There we go. 4 grams of hydrogen would react with 32 grams of oxygen to form 36 grams of water. That's the law of conservation of mass, meaning that the mass of the reactants, the amount that reacts, the mass of the reactants, is equal to the mass of the products. 4 plus 32 is equal to 36. So we want to be able to show that in terms of chemical equations. And the way we do that is by balancing chemical equations. So let's come back to our hydrogen and water reaction. I'm sorry, hydrogen and oxygen reaction to form water. Okay, so if you were to look up the masses of these particular substances, what you would find is that the mass of one molecule of H2 would be 2.02 AMU. Now, how do I know that? You look up in the periodic table that each hydrogen is 1.01 AMU, but there's 2 hydrogen atoms, so that would be 2 times 1.01, which would be 2.02. Now for the oxygen, each oxygen weighs about 16 AMU, but it's O2, so there's 2 of them, so that would be 32 AMU. So based on the law of conservation of mass, what would the mass of the water have to be? Yeah, it'd be 34.02, right? Because it's 2.02 plus 32. That's 34.02. That's what we would think. But how much does one water molecule weigh? Does it weigh 34.02? 2 hydrogens, 2.02, plus 1 oxygen, 16.00, and you get 18.02 AMU. What's going on here? This is not equal to 34.02. This seems like a violation of the law of conservation of mass, and it is actually. So in nature, what happens is elements or atoms are conserved. So if we have 2 hydrogen atoms here and 2 oxygen atoms here, here we only have 1 oxygen atom. So one of those oxygen atoms disappeared. So the way we deal with this is in the following way. Physically, I'm going to show you how this would work. Here's an H2 molecule, 2 atoms. Here's an O2 molecule. I'll show them a little bit bigger. The oxygen atom's a little bit bigger. What happens is water has 2 hydrogens and 1 oxygen. So what happens is 1 oxygen atom combines with 2 hydrogen atoms to give you a water molecule, right? H2O. But what about the other oxygen? It needs another H2. There needs to be a second H2. And that oxygen atom combines with these two hydrogen atoms. But notice that makes a second water molecule. Now you have a second water molecule. I'll call it number 2. So in fact, what you need are 2 molecules of hydrogen, and we're going to indicate that by putting a 2 in front of the H2. That means that we have 2 hydrogen molecules. We only need 1 oxygen molecule, right? 1 O2, so we're just going to leave this as O2. Even though there is nothing written in front of it, you can think of this as meaning that there's 1. There's 1 O2. And then on the water side, we need 2 of the waters, so we put a 2 in front of it. And these are called coefficients. Memorize that word. These are the numbers that go in front of the chemical formulas or the symbols of the elements. The coefficients would be 2 for hydrogen, 1 for oxygen, and 2 for water. And they essentially now takes care of our mass issue. 2 molecules of H2 would weigh twice as much as 1. So that would weigh 4.04 AMU. 1 oxygen molecule would weigh 32.00 AMU, 00 AMU. 2 water molecules would weigh 2 times 18.02, which would be 36.04. So now look what happens. The reactant side weighs 36.04 AMU. The product side weighs 36.04 AMU. They do equal each other. We've met this requirement of the law of conservation of mass. Isn't that awesome? So what we do is we use coefficients to balance chemical equations based on this physical principle. Now, many, if you ask this yourself, you wouldn't be the first student to ask this. Probably 100 million people have asked this exact same question over the years, which is, can you change the coefficient? I'm sorry, can you change the subscript in order to balance an equation? It seems appealing. So for example, there's 2 hydrogens here and 2 over here, but there's 2 oxygens and only 1 oxygen. So why don't I just do this? Change that subscript to a 1. Get rid of one of the oxygens, and that balances the equation. This would weigh 2.02 AMU. This would weigh 16 AMU. And this would weigh 18.02 AMU, and we have a law of conservation of mass is now working. The problem with that is nature. That's usually what the problem is, that we have to obey the laws of nature in this case. It turns out that that subscript is very important in terms of what the properties of a substance is or are. This is what we would call atomic oxygen. This is what we would call molecular oxygen. This is what we would call ozone. And this is what we would call tetraoxygen. And chemically speaking, they are very different substances. They do not behave the same. So the oxygen that is undergoing the reaction in nature is O2. It's not O, it's not O3, and it's not O4. Those are different substances that we could find, but they would not be the ones that are involved in the metabolism of our bodies, for example. So we have to use the chemical formulas that we have here in order to balance these equations. We cannot change the subscripts in order to balance an equation. So let me write that over here. Do not change subscripts to balance equations. In other words, change the coefficients instead. Those we're free to do, because that's just changing the amount. So for example, if I'm making Kool-Aid, I can always add more sugar, but I can't change a sugar molecule into a benzene molecule, right? Kool-Aid has sugar in it. I can't change the chemical formula of sugar. So we can change the coefficients, the amount, but we can't change the nature of that material, okay? So keeping that in mind, what we do with the rest of this particular section is we just practice balancing equations, okay? We just practice balancing.